Hey guys. Okay, so I'm back for this week, and I know that you have absolutely no reason to believe me on this, but these are actually going to be pretty short videos, or at least in the sense that there won't be many of them, because all I'm going to do is finish up what I didn't get to last week. So, in other words, I'm going to finish up by talking about problem sets from 2.4, and then I'll finish up the notes on 3.1. So, that's literally all that I'm going to do. So, it really shouldn't take too long. But if we go back to thinking about 2.4, I know it was a while ago, but that was the one that was like on inverses or it was on invertibility. That whole chapter was on that, but it was sort of the most specific, and it kind of really talked about how to find the inverse of functions and all that kind of stuff. So first I'll do like a really short example that will kind of remind us how that even works. So, whoops. So for example, if we're given a function 2, 3, 5, 8, and then we want to find the inverse of that. First, we have to figure out if it's invertible. It's a 2 by 2, which means that we can use this idea of AD minus BC, the determinant. And when we do that, we get the determinant is 1, because that would be equal to 2 times 8 minus 3 times 5. So once we've done that, then we move into finding the inverse. The way we do that is we set 2, 3, 5, 8 on one side. And then on the other side, we set the identity matrix for a 2 by 2. So 1, 0, 0, 1. And then we solve, we just move everything over. So for example, in this case, we'd start here. I'll do a really quick reminder. I won't do the whole thing, but I'll do a really quick reminder of this sort of arithmetic kind of thing, since it might have been a little bit of a while. But we would divide by 2, right? So we get 1, 3 over 2, 1 over 2, 0, right? And then we want to get rid of this 5 so that this is by itself. So we would take the 5, 8, 0, 1 and subtract some variation of this to get that. But once we've gone through that whole arithmetic process, what we would end up with is we'd have 1, 0 on 0, 1 on the opposite side now. And on the other side, our inverse, which would be -7, -3 over 2, -5, and 1. So that's just a really basic example of reminding us how we're actually supposed to do inverses. And now we'll get on to the interesting stuff. I will quickly first talk about finding this on the calculator. So if you want to find the inverse on a calculator, there are some simple steps that you do. So you click enter. Okay, so you can look this up if you need to, but basically you're going to enter a matrix. And the way that you do that is you do second mode, second matrix, and then under names, you select a matrix, and you select, under names, you select a matrix, and then you do that matrix. Here, okay, I'll write it out. So you enter a matrix. Right, like the first thing that you need to do is you need to be able to write a matrix on your calculator. The way that you do that, so you go to second mode. Then you go to second matrix. Then you go to names. You select a matrix. There will be options that say like, it'll be like A, then below that, there'll be like B, C, etc. You pick one. You enter in numbers. Then you sort of go back out and you type in the operation into your calculator, whatever matrix you've done, to the -1, and then you press enter, and that will give you your inverse matrix. So I just wanted to point that out because, obviously in the real world and here, I'm not sitting there doing all those examples. And I'm not doing them by hand. So it's helpful to know how to do this on a calculator. Okay. All right, so the next matrix the next thing that I'm going to be doing is talking about this one problem that basically says, if you want to determine whether a square matrix is invertible, so if you want to figure out whether a square matrix, a square M, as I'm going to say, is invertible, you actually do not have to bring it into the reduced row echelon form and do AD minus BC all the time. Instead, what you can do is you can reduce A to an upper or lower triangular matrix. TM stands for triangular matrix here. So you reduce it into that using elementary row operations. And from there, what we're about to prove is that you can look at the diagonal, right? And let's take a random matrix. We're going to say ABC 0D E 0 F. This is a random matrix, right? It's a square matrix. So what you need to figure out, the way that you know that it's invertible is that none of the entries along the diagonal are 0. If any of them are 0, it's not invertible. So let's look at why this is. The first thing we need to think about is this idea of cofactor expansion. So something we haven't talked about is how to use the determinant to determine if something's invertible if it's not in a 2x2 form, right? Well, there's a way we can do that, and it's called cofactor expansion. So I'm going to show that. So we're going to say that we start out with this very general matrix. We've got A11, A12, going all the way to A1n. And of course, it's in that triangular form. That's why we've got all these zeros going on. That shouldn't be 0. This should be an N, M. So A, N, M. Okay, so we've got this very basic matrix. So let's say we want to find the determinant. There's a formula. What you would do is you would take -1, and you're gonna start right here. You're gonna start at A11. You're gonna take -1, and you're gonna raise it to 1 plus 1. The way that you get these numbers, the 1 plus 1, is because we're at the term A11, okay? You're gonna raise that, and then you're gonna multiply A11 times, and here's where it's a little tricky, pay attention, times all of this. Basically, these two rows get canceled out, and you're left with this. So multiply it times A22. Right? You end up with 0, A, N, M. Right? And then you would keep doing the same thing. So this time you'd be starting with A2, 2, right? And the idea is that you do this until you get all the way down into a form where the matrix you're left with is a 2 by 2 matrix, right? And that's how you find your determinant, because now you're in the form of a 2 by 2 matrix. But let's bring it back to this idea of finding invertibility. So if you bring it all the way down, what you're really going to end up with, the last term you're going to end up with to make it invertible, to make it a 2 by 2 matrix, is A of n minus 2 times m minus 2. And I'll explain why this is in a minute. With the matrix of A n minus 1, m minus 1, a n plus m, a 0, oops, 0, and a n m. Now, if you think about it, the reason why this is, so the last thing we need to think about is the a n minus 2, m minus 2. What that would really be doing is making sure that you're going over to, up to, right? And then you'd be multiplying it times, of course, those two, that column and that row would cross out that the a n minus 2 and a m minus 2 is in. So then the matrix you'd be left with is a n minus 1, m minus 1, a n plus m, and then 0, a n m, right? Because you just have, you know, it'd be one below, it'd be one less of both rows and columns than this right here. So this would be what you'd end up with if you kept going down and down and down and down and down through this cofactor expansion. Now, imagine trying to find the determinant here. You multiply this and this and this and this. Well, of course, we know that this would immediately cross out. Well, let's think about this though. What is this? What we do know is both of these things are on the diagonal, right? Because if you think about it, you know, we know a n m is because it's the farthest to the right and the farthest down, right? And then so is this because it's proportionally, it's in the diagonal to that, right? So what you end up with is you're multiplying the diagonal, right? And then you're also, the a n minus 2, a m minus 2 is also on the diagonal, right? So you end up with this final matrix where, or with this final kind of equation, expression or whatever from cofactor expansion, which is supposed to be a way of finding if something is invertible, that gives you, you're multiplying something on the diagonal times both of these things, right? And then both of these things have to be multiplied times each other to get your determinant, right? Well, if any of these things is 0, then your determinant immediately becomes 0, right? So that means that these three things can't be 0, and these three things are on the diagonal, right? So if we return back to that idea that we had of A, B, C, 0, D, E, 0, 0, F, it's written very poorly. This is just an example matrix of arbitrary size, right? But if we turn it back to that, these three things on the diagonals, basically, they can't equal 0. We've seen what happens if they equal 0. The determinant ends up equaling 0. So if we don't want to go through the whole process of cofactor expansion, if we've got a square matrix, then we can know that the determinant is just going to be the things on the diagonal, right? So the things on the diagonal, if any of them are equal to 0, or in other words, they're equal to the product of the things on the diagonal, right? So if any of these things are 0, then obviously, you know, it's not going to be invertible, because if we think here, we're taking one thing on the diagonal, we're multiplying it by both of the things, by the two other things in the diagonal, they're being multiplied times each other. We're multiplying parts of the diagonal by each other, and that's determining what the determinant is. So, if any of these are 0, then the determinant is going to be 0. So if you've got a square matrix, you can know that it's not invertible if any entry along the diagonal is not 0, or is 0. Of course, you have to put it into that upper or lower triangular form first. That's very important. So just like you have to put a 2x2 matrix into reduced row echelon form, like you got to put it into triangular form, because part of that whole cofactor idea was that we knew these couldn't equal 0 because this right here did. So that means that this whole part of the determinant did. So that's sort of a little proof there that will hopefully be helpful later on. The next question that I've got is number 37. I know that doesn't mean anything to you because you don't have the textbook, but it's number 37. And we know that A is invertible. It's an invertible matrix. And we know that C is a non-zero scalar. What we want to know, though, is if matrix C A is invertible. And if that's true, we want to know the relationship between inverse A and inverse C of A. So the first thing we have to realize is for A to be invertible, that basically means that we've got C A equals C of A, B, C, D, right? Of course, this is just an example. It's a matrix of arbitrary size. We have no idea how big it is. So, it might not be a 2x2, but we'd end up with the determinant C, A. Nope, that's not an eraser. This is an eraser. Okay, so we'd end up with a determinant of C, A, C, D minus C, B, C, C. And that could not equal 0. Let's think about this. What were the conditions that we would have to have for this to not equal 0 and therefore to be invertible? Well, we can pull out C, right? Actually, we can pull out C squared. We have C squared times AD minus BC cannot equal 0. Well, let's think. We already know that AD minus BC doesn't equal 0 because we know that A is invertible. And we know that C is a non-zero scalar. Now, is there anything that can be squared to equal 0 if the original number is not 0? No. So that means that this right here is not equal to 0. So that means we're multiplying a non-zero number times another non-zero number, which can't equal 0. So in other words, CA is invertible. But let's move on to talking about the relationship between the two of them, right? So if we have CA and we take the inverse of it, let's write this out. The trouble I got into was assuming and not writing things out. I think that's one of the things I'm learning is that you kind of have to write everything out. Even if you think you know something, you need to write it out and try to prove it. So if we've got the matrix CA, CB, CC, CD, and we're finding the inverse of that. Let's find the inverse in terms of the determinant. So of course the inverse would be 1 over C squared AD minus BC, then times CD negative CB negative C, 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 A. Okay, so immediately what you should notice is that we can pull out C's, right? We can pull out all of these C's. And if we did, that would look like C over C squared of AD minus BC. And please don't get the two C's confused. I know it's a little annoying, but this C is referring to the scalar. This one's referring to the component of the matrix. But anyway, D negative B, C negative C, A. Okay. Well, now the next thing you should immediately notice is that this can be crossed out, and in its place of 1 over C, right? Now this whole thing could be characterized as inverse A, right? Because if we didn't have this whole C thing going on, right, this would be just what we would do to find the inverse of the A. So what we're left with is 1 over C times A inverse. Well, what's 1 over C? Well, if we just take a normal scalar, not a matrix, and we find its inverse, it's going to be 1 over that number, right? So in other words, we've got inverse C times inverse A. So here's a relationship. The relationship between inverse A and inverse CA is we've got inverse A, that becomes inverse C times inverse A. That's our final relationship. Okay. Is there anything else? Oh, yes. There's one more teensy tiny little problem. It's so small, y'all. It's absolutely tiny and it will take 3 seconds, I swear. This is a true false question. There's a section where they were like, are really not true false, but verify if these are true. So they give us this equation, a plus b squared equals a squared plus 2ab plus b squared. Okay, so something should immediately stick out to you, and that should be this 2ab. So the reason why is because let's actually do this. Let's take a plus b and multiply times a plus b. So we're getting back to our algebra 1 pre-algebra roots with our distribution method. So what we would get is a squared plus ba. Sorry, plus, that's not correct. Don't want to make the same mistake that the book did, plus ab plus ba plus b squared. Okay, so what the book did is it added these things together, right? It added ab and ba. But can we actually do that? Well, let's go back to one of the things that you may have forgotten, but that we did learn in this chapter, which is that matrices are not commutative. And matrix multiplication, it's not, matrix multiplication is associative, but it's not commutative, right? Which means we just can't move things around wherever we want, you know? We can group things however we want, we can't move things however we want. So that means that we can't actually add a, b, b, a, because they're not the same thing. They're in a different order, which means that they're equaling different things because matrix multiplication isn't commutative. So we can't actually add those things to get this. So that makes this false. That makes this equation wrong. It's not true. Okay. So those are just a couple of examples. I just wanted to kind of get to these to explain some more things. I think it was important to talk about cofactor expansion. I think it was also important to talk about making sure that we write things out fully when we're trying to look at relationships between things. I reminded you about just general finding inversions in case you've forgotten. I reminded you or showed you how to use the calculator to find inversions quickly. And then I also reminded you about commuting. And yeah, that's kind of all the important stuff from what I did in the 2.4 problem set. So I'll stop here. I'm going to come back with the end of 3.1, which is just about kernel and should be really short and snappy.